Yep.
Yeah, so I explained kind of the math behind how braids work a little bit, and hopefully this makes sense. There's different ways of looking at them. So now I want to tell you a little bit about like why people care about this outside of just math, and it actually has multiple applications. Also something that I wanted to show you. There's an entire field of topology called knot theory, and essentially what this is it looks like this. So what knot theory is it's like a part of topology which studies these things called knots. And the way that they're related to braids is, imagine you take like the two bottom strands, for example, the thing that I'm pointing at, and the two top strands, and you put them on top of each other. So you loop the braid back on itself. You're going to get that knot. So in some sense, like braids and knots are just two sides of the same coin. Yeah, this is also kind of like a separate topic which has a lot of interesting stuff associated to it. And yeah, one thing that I wanted to show you is actually more about knots than braids. And one of the main like really cool applications is in physics, specifically like in theoretical physics. And I actually became interested in this topic because I like mathematical physics, and that's how I started. So imagine you have some like particles, or let's just say you have one particle, and this particle has some kind of charge, right? If you have another particle that has charge, let's say we're going to move the charge like this, then the way that these are going to be moving together will be related to their charge, right? They're going to move in some kind of dance around each other. And in classical mechanics, when we want to show how one particle is moving, it can only have like one possible path, right? It just moves in some kind of line. Like imagine this is a cannonball. It just moves from like A to B. So this is just the start, and this is the end. And I'm not going to go into like why this is true, but in quantum mechanics, this isn't really true. A particle can have multiple different paths instead of just one. So its path is actually going to look something like more like this. Like this is one possible path of the particle. And again, the particle is charged, meaning that it'll be moving in some kind of like field by virtue of its interactions with other particles. So yeah, in quantum mechanics, we have this idea that there's multiple possible paths a particle can take, and every single path has a probability amplitude associated with it. So the likelihood of it going in some direction is probabilistic, kind of fundamental. And one way that the paths can arise is it can actually move in a knot. So this is kind of hard to draw, so please bear with me. So yeah, one possible path that a particle can take could be in a knot, which as we saw is just like a braid which is looped back on itself. And yeah, there's like a bunch of different, there's a million different knots that you can have. Like the most basic one is this, and this is called the trefoil knot because it kind of looks like a clover. So yeah, basically just imagine like a piece of string which is somehow looped back on itself, it's a knot. And yeah, when physicists try to study the paths that a particle can take, they need to sum over all the possible paths, right? Because as we saw, there could be multiple different ones. And the particle can be, the path can be knotted. So let's say that this path is called path K, and we want to find out what the probability of this path is. It's pretty complicated to say like exactly how physicists calculate this, but essentially the probability amplitude associated to some path is calculated through an operator which is called the Wilson operator, and we can just denote it WK. And Another thing that you can do with different knots, in the same way that we were trying to figure out if different braids can be the same by virtue of like where the crossings occur, is you can try and look for invariants of this knot. So what are the properties of this knot that like no matter what I do with it, they'll always remain the same. And if we show that, for example, two different knots have two different invariants, so also like with the fundamental group, that was like a topological invariant, and that means that those knots are definitely different. And there was a Fields medal that was given, I think, in like the 60s. It's a guy called Jones, and what he showed is that every single knot, kind of by counting the different crossings and how they occur, you can have a polynomial associated with it. And it's called the Jones polynomial. And this polynomial is like an invariant property of different knots. So a given knot only has one polynomial, and if you find a knot that has a different polynomial, then it's definitely a different knot. And yeah, I'm not going to explain like, how you calculate this, just accept this as being true. And yeah, it turns out that the way that you calculate the probability amplitude of the path, yeah, the Jones polynomial for like this given knot, given that this is a path, is going to be the average of the operator. So essentially what this means is like the likelihood of a particle moving in a certain way is directly related to how many like knots and how complicated the knot in its path is. So there's like a super clear link between the topology of the path and the likelihood of it occurring, which I think is pretty interesting. And yeah, then also obviously braids can be used in biology. If you think of DNA and how it like loops over each other, the braids fit that structure super well, super nicely. And then the last thing that I want to mention is cryptography. So let's say we have like the classic Alice and Bob, and she wants to send a message to Bob. What Alice can do is she's going to take some braid. Let's call it X. And this is going to be her private key. So nobody else knows what this braid is. And then she takes a public key, which is going to be some other braid, and we're going to call it A. And then she's going to generate a new braid through composition, and the new braid is going to be called B. So the reason why this works is kind of in the same way that in RSA cryptography, the reason why it works is because it's really hard to factor out like prime numbers. If you have these really big, complicated braids, it's hard to figure out what like the factors of it are. But if you know the public key and you know what the private key is, then this becomes really easy. So this is one way of encrypting messages. And yet this is computationally hard, and at the moment it appears to be NP. Which if anybody isn't familiar with what this is a complexity class, which basically tells you like how difficult it is to solve a problem. And that can be measured either in like the amount of storage that a computer needs to do that, or the amount of time that a computer needs to like, break this algorithm. And since it appears to be NP, meaning that it's like hard, this is one way of encrypting messages. So yeah, that's it. Thank you for listening, guys.
So, yeah, okay, I'll do like a quick ending, and then this is just for official me. Okay, thank you guys, thank you ladies and thank you gentlemen who come to our talk today, and yeah, thank you David. Please once again give a big clap to David. Okay, and I hope everyone enjoyed today's event, and then see you guys next time.
Thanks, guys.